Okay, so let's get started. Let's continue on the work we did yesterday. Still working on chapter 3, section 4, factoring polynomials. So, as a general concept, whenever you're asked to factor a polynomial, up to now, I don't know if you've noticed, but just about every polynomial you've ever been given has been a quadratic. Right, something like 3x squared plus 4x plus 7. I don't know, something like that. It's a quadratic power 2. If you ever run into something bigger than that, there's been some very special cases, right? So like maybe, for example, it's a hidden quadratic. Like maybe it's 4x to the 4th power plus 2x squared plus 7. And so now it's kind of a hidden quadratic because what you can do is a substitution where you let this x squared be squared, there's a 4 there, plus 2x squared plus 7, and now you can do a substitution, let w equal x squared, so now you have 4w squared plus 2w plus 7. So you thought you weren't working with quadratics, and then you kind of were working with quadratics. And then another case, quadratic form, like maybe you thought you were working with something degree 3, 2x squared plus 7x. Like, oh, this isn't a quadratic, it's degree 3. True, but they all have an x in common, so we can factor that x out and end up with something that goes back to quadratic. Right? Okay. Or maybe you thought you were working with something that was much bigger, like maybe x squared, like x to the 5th power plus, let's make it a 4, 2x to the 3rd power, plus, I don't know, 4x squared plus x, I don't know, just making up numbers here. And like, oh, okay, this is a 5th power polynomial. Well, in cases like this, one of the only tricks we can apply is to think about factor by grouping, right? So we group up these two, see what they have in common, a 2 and an x to the 3rd power, and then what remains is an x squared plus 2, and then we keep going, right. So I just made this one up, so it's not going to work out, but that was my point. So we can try factor by grouping. We can try factoring out a common factor. We can try maybe some sort of interesting substitution that might work out. But there were, by and large, very few cases where we had a polynomial that was of a higher degree. Right? So now if we were asked to factor 3x to the 3rd power plus 2x plus 7, say something like that, we are stuck. Right, we cannot do factor by grouping because that requires us to have either 4 or more, depends, but usually there's 4 terms, and this only has 3 terms. I can't factor the first 2 terms, factor the last 2 terms since there's only 3. They don't all have an x in common, so I cannot reduce it into a quadratic by factoring out an x. And it's not a quadratic in disguise like this case, so we're stuck, right? And up to this chapter that we just looked at, there was nothing else we could do. Right, so this chapter gives us one more tool that can help us factor a polynomial, and that's what we're doing. So we're still restricting it to polynomials that involve rationals, so it's not like we're able to factor any polynomial out there, but it will greatly expand the world of polynomials we can actually factor. Okay, so as a concept, that's what we're doing. We're coming up with another technique to factor a polynomial or to attempt to factor it by doing the work we did yesterday. Good? Okay, so for example, let's do one more example like in yesterday's style. But we're going to reverse engineer it by starting with the answer. Right, so here's the answer. Right, so for the next test, I'm going to come up with the answer. Let's say that the polynomial I want to create is x plus, I don't know, x plus 2. Let's have 2 of those squared, and then x minus 1, and an x plus 5. Like that. Let's say I have this. Well, let's make 2 of these as well. Yeah, sure. 2 of these, 2 of those, 2 of these, 1 of these. So here's my solution. When it gets all factored out, it's going to look like this. So I need to expand this whole thing out. I could FOIL the whole thing out, and that could be fun. Or I can use technology. So let me find a polynomial expansion. Polynomial. Oh, there it is. Expansion calculator. Great. Let's go with this guy. Okay, expand. Now I want to expand this thing here. So x plus 2 to the power of 2, x minus 1 to the power of... You know what? I'm going to change it. Now that's fine. Let's make it 3. Let's make it extra fun. And then I have x plus 5. Go. Expand that whole thing. Yeah. Here it is. Okay, so it's going to be this really fun thing right here. Let's put it up here. So let's erase this 2. We turned it into a 3. And now I have the expanded form, which would be x to the 6th power plus 6x to the 5th power minus 26x to the 3rd power plus 2x squared plus 36x minus 20. Let's see, is that x to the 6th plus 6x to the 5th minus 26x to the 3rd plus 3. Oh, see, messed up. Plus 3x squared. Should be a 3. 3x squared plus 36x minus 20. Okay, so this guy's a 3. Okay, so we know from our technology that these two things equal each other, right? This is the expanded form, and then if we factor this whole thing, we get that. Okay, so here's the answer, but now we need to figure out how to get that. So this is where the question would be given to you this way. Right? Factor this polynomial. Factor this guy, this right here, right? Power degree 6. Up before this chapter, there was just nothing we could do. There's no way we can factor this whole thing. Okay, but what do we do now? All right, so chapter 3, section 4 says that if we're given a big ugly polynomial like this, and we want to try and factor it, one of the techniques we can do, again, it's not always going to work, but it'll work more often. It's something worth trying. Okay, so we begin step 1 by creating a list of possible rational factors. List of possible rational factors. This list will contain a -2, a +1, and a -5, right? Because I already know the answer. I'm cheating here. But this list will include these. It'll include a whole bunch of other numbers too, potentially. But it will include these ones as well, because I already know that those are rational zeros of this polynomial. Okay, and so the list is going to be something of the form P and Q. And it's unfortunate that this P is the same as that, but you know, it's a coincidence. This P is just a variable. It could be anything. Okay, I could make it of the form A and B. It's just that your book uses P and Q. It could be a fraction of the form A over B, where A is a divisor of this 20. Divisor of the 20. It's always a divisor of the constant at the end, divided by a divisors of 1. Where this 1 comes from here. This 1, this 1 right here, is a 1 in there. and the 20 is the constant at the end here. This 20, this 20.
That's like the first and last numbers.
Correct, yeah, correct. Once you've written it in this descending order, right? So sometimes they'll trick you by moving it around, and then the x to the sixth power might be hidden in the middle somewhere. So you got to reorder it in descending order. Then it's a degree 6 polynomial. This is the leading term, and this is the leading coefficient that's out in front, which is a positive 1. Good? Okay, so all the divisors of 20, and it's plus or minus all those. So it's plus or minus 1 divides 20, plus or minus 2 divides 20, plus or minus 3 does not divide 20, 4 does, plus or minus 5, 6 does not divide it, 7, 8, 9, 10, plus or minus 10, plus or minus 20. 20 goes into 20. Luckily, in this case, there's only one case for divisors of 1. It's just 1, plus or minus 1. And then 1 dividing into all of these is just going to be 1. So in this case, we're going to have a bunch of whole numbers, no fractions at all. All right, so that's good. Let me put it over here. So it's really just these guys. It's just going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. And there we go. And again, peeking ahead, since I already know what the answer is, I know that negative 2 is in there. I know that 1 is in there. And I know that negative 5 is in there. Right? There's a whole bunch of other stuff in there. And if you didn't know the answer, you wouldn't know which ones are the answers. But they're in there. And there's just a bunch of other stuff that also isn't in there. Okay? We learned that because negative 2 is a 0 of the polynomial, right? If I plug in, meaning that if I come up here to the answer and I replace all these x's with a minus 2, a minus 2, and a minus 2. If I come back up here to the answer and replace this whole thing with a minus 2, here we're going to end up with 0 squared, which is 0, times, who cares? The rest of it gets multiplied by a 0, so I know that the whole answer is going to be 0, right? If I replace the x with a negative 2, the whole answer is 0. Because this is equivalent to this ugly long polynomial, it also means that if I replace all of these with a negative 2, it's not as easy, it's not as clear cut to see, but it will be equal to that one. So therefore, this whole thing is also going to be 0 when I replace this x with a minus 2. Right? That's why minus 2 is a 0 of the polynomial. Good? Good. Okay. So if I set this whole thing here equal to this polynomial, they're equal to each other, and I divide both sides by x plus 2, I'm going to get a new polynomial. It divides it evenly, right? We saw that yesterday as well, that because it's at 0, it must mean that x minus that constant, in other words, this binomial here, must be a divisor of that polynomial. Good? Okay, so again, we're pretending we don't really know the answer, so we don't really know that negative 2 is going to be one of the ones that works. So what do? How do we figure it out? Erase all of these really carefully. So if we don't know that negative 2 is an answer, then we've got to check them all. So this is where I would recommend we use a calculator to save a little bit of work. Otherwise, that might take forever. Okay, so let's grab our calculator. Once we create our list, the next step is to go over to our calculator. And we're going to go over to y equals, and we're going to type in this polynomial, right, the original polynomial. So let's clear. To erase everything that's already on there, hit clear and enter. That'll erase it all. Come back up. And now we can type in the one we want. So we want x to the power of 6 forward, and then 6 times x to the power of 5, enter, and then minus 26 to the power of 3 plus 3x to the power of 2 plus 36x minus 20. See, that's what happens when you don't pay attention to what you're doing. And that's why it's important to have parentheses and all that. See what I did? I put it in the exponent, and then I put that in the exponent, and it's just a big mess. Anyway, let's just start over. Clear, enter, clear. Okay, so x to the power of 6 forward plus 6x to the power of 5 forward minus 26 x to the power of 3 plus 3x squared plus 36x minus 20. Okay, good. So we type it all in there. Then we got to go to table set, make sure that the independent variable is under ask. Then we're going to go over to table, right above there. So second, graph. There's a little button that says table up there. You should get to this graphic right here. And I'm just going to delete these old values here. What's going on? Delete, 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 delete. Get rid of all these values. Did everybody get to this point on their calculator, or would you like me to review any of those steps? Okay.
You go over the steps.
Sure. We begin life by going over to y equals, right here, y equals. You get to this screen, and then you type it in, and for the variable x, you got to use this button right here. It has an x, a t, a theta, and an n, and by default, your calculator should know what function setting you're in, so it'll know that it's an x. Now, if you're not getting this, if you hit y equals and your screen looks different, that's because the mode is different. So if this isn't working out for you, this might be your fix. Go to mode, and then make sure that it says functions right here, because the other settings are parametric, polar, and sequential. So for now, we're in function mode. If it's not there, use your arrows, go down, and hit enter to put it into function mode. Good. Also under normal, float, that doesn't matter right now. Okay, so go over to y equals, type that in. Next, we're got to go to table set. And really, you only have to do this once. As long as you don't remove your batteries on your calculator, it should remember. So right above the button that says window, there's a little thing that says table set in blue. See if I can make this bigger. The little thing that says table set right in there. So we have to hit second table set, second table set. That gets you to this screen. Under independent variable, you're going to hit ask. So you got to go down, down, to the right, hit enter, make sure it says ask. Dependent, leave it as auto. This doesn't matter for us. Good? And then finally, right above the button that says graph, there's a little button that says table. So we hit second table, and then we get to this screen. What this screen is a place for you to evaluate this polynomial. It will automatically calculate what the result of the polynomial is based on the input variable x. So for instance, let's do a really easy one. Obviously 0 is an easy one. If I let x be 0, this would be 0, 0, 0, 0, 0. So I should just get a negative 20 as an answer, right? So if I type in 0 into here, 0, enter, I get negative 20. Good. Another really easy one should be 1. Okay, 1, that's 1 times 1 is 1. 1 to the 5th is 1. 1 times 6 is 6. Okay, so if I replace all the x's with a 1, I should get a 1 plus 6 makes it 7, minus 26 makes it negative 19, plus 3 makes it negative 16, plus 36 makes it positive 20, minus minus 20 makes it 0. Right? So if I type in a 1 right in here, I get a 0. Good. And that's what actually we're looking for. We're looking for the zeros of the polynomial. We already know, right, because our answer is here. We started by starting off with the answer. So I knew 1 was going to be the answer. Anyway, this table setting now allows me to evaluate the polynomial at all of the other values really quickly, really easily. Right, so I tried 1. Now let's try the rest. Let's put this over. It's too big. So that we tried 1, let's try negative 1. Negative 1 fails. How about 2 fails? How about negative 2? Negative 2 worked. How about 3? No, 4. 4 is going to fail. Negative 4 is going to fail. How about 5? It's going to fail. How about negative 5? Negative 5 works. Right? And then, well, if you don't know that that's the answer, you wouldn't know you're done. You got to keep going. So try 10. Nope, that's not going to work. How about negative 10? Nope, that's not going to work either. And then finally, you only have a couple left. Now, the other thing is, I think this thing doesn't want to do more than these values. I think it starts replacing them. Let's see, negative 20, so 20. Yeah, see how it used to be negative 10 here? Okay, anyway, your calculator might let you scroll down and put more values, but this one doesn't let me do it. I don't know how to change that. Okay, so I tried them all, and you see that the only ones that work, the only ones that give us a 0 are positive 1, negative 2, and negative 5, which is exactly what we expected. Negative 2, positive 1, and negative 5 are the zeros of this polynomial. Good. So let's keep going. From our calculator, there's a step 1, create this list. Step 2, step 1, create this list. Step 2, from calculator, I know that P of negative 2 is 0. P of positive 1 was 0. And P of negative 5 is 0. From here, this must mean that x plus 2 is a divisor. Divisor of P of x, right? Of x to the 6th plus 6x to the 5th minus 26x to the 3rd plus 3x to the 2nd plus 36x minus 20. Right? That's what that means. This will divide that because it's a 0 of it. And same thing with the other ones. This must mean that x minus 1 is a divisor of this ugly polynomial. And it must mean that x plus 5 is also a divisor of this ugly polynomial. Now, in the examples I did yesterday, it just so happened that every example we did, we found every unique 0, meaning that all of these powers were 1, right? I think in both examples, the given polynomial was degree 3, and then we found 3 zeros, and then I just jumped to the answer and said, oh, just multiply them all together, and that's your answer. That won't always work, and that doesn't work here. Because notice that if I decide, oh, here are my zeros, and then I decide, oh, this is just equal to the multiplication of x plus 2, x minus 1, and x plus 5, that's not the answer because I'm missing the exponents. I don't know that x plus 2 needs to be squared. I don't know that x minus 1 needs to be cubed. And I don't know that x plus 1 is raised to the power of 1. Right? So I still need these guys right in here. So how do we get them? How do we know that that's not it? Well, we're going to have to do the heavy lifting and actually divide it. So we know that these are divisors of this thing, of this polynomial. So we're going to have to actually divide it. Right? So we can use synthetic division. let's begin by maybe this one. 1 is usually the easiest thing to work with. So divide x to the 6th power plus 6x to the 5th power minus 26x to the 3rd power plus 3x squared plus 36x minus 20. Let's divide that whole thing by x minus 1. We could do it the long way, polynomial long division. We could use technology if you're sort of allowed to use technology, but then that begs the question, if you're allowed to use technology, why not just tell the calculator to factor that whole thing, right? I mean, it could do it. So we're going to have to do it the old-fashioned way. So let's use synthetic division. So to divide this, we're going to do 1 goes into synthetic division. Note that all the powers are represented in descending order. 6, 5. Oh, wait a minute, it's missing a 4. Right? So 4 is missing, so we're going to have to introduce a 4x to the power of 4 somewhere in there. Right? So we have the 4 represented. 6, 5, 4, 3, 2, 1, 0. Okay, so it all works out. So now I'm going to copy those those coefficients in front. There's a 1, then there's a 6, then there is a 0, then there's a negative 26, then there's a positive 3, then there's a positive 36, then there's a negative 20. Okay, synthetic division, bring this guy down, we get a 1, multiply them together, we get a 1, add them together, we get a 7, multiply them, we get a 7, add them, we get a 7, multiply them, we get a 7, add them, we get a negative 19, multiply them, we get a negative 19, add them, we get a negative 16, multiply them, we get a negative 16, add them, we get a positive 20, multiply them, we get a positive 20, add them, we get a 0. Right? The nice thing about this is we already expected this to be a 0 because we knew that this was going to be true. This divides that, which means the remainder is 0. If you don't get a 0 here, that means you did something wrong. We're good so far? Okay, so that means that when I divide this, it's going to give me a new polynomial of degree 5 because this has degree 6. So degree 5 where these are all the coefficients. So far, I've established that this is true. The original polynomial given, minus 26x to the 3rd plus 3x to the 2nd plus 36x minus 20 is equal to x minus 1 times, and then I'm going to take all these coefficients and do a polynomial with degree 5. So it's going to be x to the 5th power plus 7x to the 4th power plus 7x to the 3rd power minus 19x squared minus 16x plus 20. Is that okay? Any questions about this? No? We're okay? So I've chipped away at it. I started with this ugly polynomial of degree 6. The instructions were to factor it, and after a whole lot of work, we were able to reduce it down to this binomial times this polynomial of degree 5. So we've chipped away 1 degree down. 1 degree down, 5 more to go. Good? Okay, so now we also know that 1 was a 0. We also know, let's work with 2 now, negative 2. Negative 2 is a divisor, which means that this is also going to divide our polynomial. Now we can start off with, we can go back to the original one and divide it, instead of dividing the original one by x minus 1, we could divide the original one by x plus 2, and that will give us an answer, but that's not going to be useful. It's kind of like this. Let's say that you wanted to divide or factor the number 240, right? And then you're like, oh, somebody tells you, oh, this is divisible by 2. Divisible by 2. and also by 5. Right? So you have those as your divisors. If you go ahead and do the work, you actually go through the work of dividing this by that, right? You do, okay, 240, 240, 240 divided by 2. Okay, so you do all this work and you get that that's 120. Okay, so then you get to say that 240 is really equal to 2 times 120. That's equivalent to what we did here. We have our polynomial. We knew this was a divisor, so we divided it. We got our resulting polynomial here, our quotient of the division. So that means that the divisor times this quotient equals to the original polynomial, right? Just like here, 240 is divisible by 2, so we divided it, and we get that our result is 120. So that must mean that 240 is equal to the divisor, which is the 2 times the 120. Great. They also tell you that 5 is a divisor of that. Now you could go back to the original and divide these two, right? And figure out what this is. And then you would end up with 240, right? If you go 5 goes into 240. What is that? Why am I having a brain fart here? 20, 40, 45? Wait, that looks weird. Is that right? 45 times 5.
48, maybe?
48. Yes. Okay. Need more coffee. 48 times 5. Yep, there you go. So you do all this work and you figure out, okay, 240 is equal to 5 times 48. But if you're trying to factor the polynomial, dividing the 240 by 5 isn't as helpful. What you should have done is divide this guy by 5 so that you can further figure out that it's 2 times 5 times, why am I having such problems with this? 24 times 24. Does that make sense? Okay, so my whole point of all that is that I know that x plus 2 is going to be divisor of this polynomial, but I don't want to divide this polynomial by the x plus 2. I want to divide this one. The new result when I divided the x minus 2 and I got this as the quotient, this guy needs to be divided now by x plus 2 to further break down the factorization of the original polynomial. Questions? 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 That makes sense? That makes sense? Good. Okay, so let's use synthetic division to do that. And we have that it's got to be a minus 2. And then it's going to be a 1, a 7, another 7, a negative 19, a negative 16, and a 20. So since you see I just have to work with this, a lot of people just pick up on this. When they do this, they just build onto it right here and maybe just grab onto this thing and then do a minus 2 right here, and then they do their work here. And as you can see, you can probably imagine the next one is going to be to do it with a minus 5. So you get an answer from here, and then you got to do the minus 5, and just kind of begin to chip away at it until you get the whole thing. And there's some other kinds of notational shortcuts that are also popular out there. Some of you guys might be familiar with them. They're all derivatives of the same thing. Okay, so we put a 2 there, minus 2, that's a 5, that's a minus 10, that's going to be a minus 3, that's going to be a positive 6, that's going to be a negative 13, that's going to be a positive 26, that's going to be a positive 10, that's going to be a negative 20, and there, you get a 0. Good. So bringing those two together now tells me this is what we have so far. X to the 6th power plus 6x to the 5th power minus 26x to the 3rd power plus 3x squared plus 36x minus 20 is equal to, almost looks like an equal sign, minus 20 is equal to x minus 1 times x plus 2 times this as the resulting polynomial of degree 4. Right? We're slowly chipping away at this thing. Degree 4 plus 5x to the third power minus 3x squared minus 13x plus 10. Good. Next, we know that x plus 5 must also be a divisor, so let's try that one. Right? So from up here, we know that x plus 5 is also a divisor of that. So it must also be a divisor of this. So let's use synthetic division to divide this guy. Divide by x plus 5. So like I said, most people, or a lot of people, then just work on this right here. So let's just do that right here. So let's just put it in red so it stands out. Okay, so I'm just going to work with this, and I put a minus 5 there. And so this will be a 1. Carry that forward. That's minus 5. That's going to be 0. That's going to be 0. That's going to be minus 3. It's positive 15. That's going to be a positive 2. Makes it a negative 10. Yep, exactly what we thought. It's a 0. Good. Okay, so from this work now we're even closer to getting our answer. We have that this is x minus 1 times x plus 2 times an x plus 5 x plus 5, and then we have an x to the power of 3. Now we could put that plus 0x squared, but I'm just going to put a minus 3x plus 2. We're good so far? Okay, we tried all 3 of the zeros that we know about, and we're still left with something, right? Some other thing. What we have to do now is check to see if that 0 appears more than once, as we already know it does, right? Because we're kind of cheating. We already know the answer. We know that the answer is that the x plus 2 appeared twice and that the x minus 1 appeared 3 times. So it can further divide it into that, right? Just like when we wanted to factor 240, 2 goes into it there, but then 5 goes into it there, sure. But then 2 goes into it again. 2 is another factor. 2 appears more than once in the factorization, the prime factorization of 240. Right? But, you know, that's kind of unknown to us, so we're just going to have to try different things out. Once we've expanded it to this form, let's try these again and see if they work. Good? And remember, once we get to a quadratic, it might be something we can factor by one of our other methods from before this chapter. So we're one chip away. If we can get this to a quadratic, it might turn out to be something we can factor. Okay? Why not try 1? Usually 1 is the easiest thing to work with. So I'm going to try to divide this thing. Let's put it in green. Divide by one of these, and it doesn't matter. If you don't know what the answer is, then you're just kind of blindly checking. If it turns out that if I try and divide it by this one, it's going to fail. It's not going to give me a 0 at the end, because it turns out that this should only appear once in the prime factorization of that polynomial. But if I try either one of these, it's going to work out, right? So let's try the x minus 1. By default, I would try the one with the smallest number. 1 is usually a nice, easy thing to try. So I'm going to go back to this guy up here and put it there. Here's my 1. And then 1 goes there. 1 goes there. That makes it a 1. That makes it a 1. That makes it a minus 2. That makes it a minus 2. And yep, a 0, just like I expected. That means that this is another factor of this guy. Okay, so now armed with that work, now we have the following. Now we have that the original polynomial is equal to x minus 1, and then we did an x plus 2, and then we did an x plus 5, and now we did another copy of x minus 1, and the resulting polynomial is this one, degree 2. So it's going to be an x squared plus x minus 2. Good. Questions, 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 questions? And now we're at the quadratic level. We could keep going and repeat the process if you forget. And again, we want to keep going with dividing things, right? So now let's try dividing this, divide by one of these guys. Maybe x minus 1 appears again. Maybe x plus 2. Maybe x plus 3. Keep dividing them. If you divide it by all three and none of them work, that means that you've gotten to a point where it no longer factors nicely. Maybe the answer involves imaginary numbers or something, right? So you might have to go to the quadratic formula at this point. But in this case, it's something that factors nicely. So divide by x minus 1 or x plus 2 or x plus 5. So that's how you would keep going to figure out what that is. But otherwise, since it's a nice quadratic, we know that this factors into the form of x plus blank, x plus blank multiplies, two numbers are multiplied in negative 2, but add the positive 1. How about plus 2 and minus 1? Right? Minus 2, positive 1. There we go. So that's what this is. And then we bring it all together. We have an x plus 1. Oops. X minus 1, x plus 2, x plus 5, x minus 1, right? So that's from these guys. And then these factored into that. And then we can put it all together and say that there are 1, 2, 3 copies of x minus 1. X plus 2 has 1, 2 copies of that. And there was only 1 copy of x plus 5. So there we go. All that work to figure out that the factorization, p of x, the original polynomial, which was x to the 6th power plus 6x to the 5th power minus 26x to the 3rd power plus 3x squared plus 36x minus 20. That whole ugly polynomial is equal to the product of these binomials. Good? Any questions? No. Okay, so this gives you a really powerful tool to help you factor polynomials, but it's not always going to work. It's not always going to work out because the prime factorization of this thing could involve a bunch of imaginary numbers. So that's a problem. If it only involves 2 imaginary numbers, so if we can get it down to a quadratic and then the answer to that quadratic involves imaginary numbers, then that's still very doable, right? Because you can chip away and get to that quadratic. And then once you get to that quadratic and you're like, oh no, that just involves some imaginary numbers, we can use the quadratic formula and that can help us find it, right? In this section, we're not really going to do that, so don't worry about it. However, if the prime factorization involved lots of imaginary numbers, then we're in trouble still, right? So another thing that can go wrong is that maybe the prime factorization involves irrational numbers. Remember, this whole thing was about a list of possible rational zeros. So in other words, if I gave you, if I'm, coming up with a really hard test question, and I go, okay, I really want to trick my students, instead of working with this and expanding it, what if it involved pi? What if I had this squared and then x minus, how about root 3 to the 3rd power, right? So say, and then some imaginary numbers in there. 3 plus 2i as an imaginary number, and therefore it must also have 3 minus 3 minus 3 plus 2i say I had this whole thing. I have some imaginary numbers. I have some irrational numbers. This thing is really ugly. And this process we just described really wouldn't help us too much with this, right? Especially if this was raised to certain powers, right? So then maybe this guy is also raised to the power of, I don't know, raised to the power of 4. This raised to the power of 2. You know, this thing's really, really nasty. So in a case like this list of possible rational zeros really wouldn't help us. Okay, good. But we won't face any of this, so don't get scared by this crazy stuff over here. I'm just pointing out that though this is a very nice, powerful tool, it won't always help. It's really nice. It's really helpful when it factors into some nice, pretty fractional, rational, fractional and rational are the same thing, rational zeros, like a 2 or a 4/3, something like that. Okay, any questions? Questions? No? We're good? Okay. All right, so that ends our focus on to chapter 3. We're going to stop there. Let's look at where we are with that. Yeah, so the whole point here in this section, this is section chapter 3, section 4, is to really factor these polynomials, and then once we factor the polynomials, we can tell what those zeros are, and that's really helpful in many situations, right? The zeros of a polynomial are also the x-intercept points, and then in a lot of word problems, those are important, like figuring out where those zeros are. So it's a nice tool to have in your pocket to be able to factor a polynomial out and be able to find those zeros. So now the textbook, likes to pretend you have absolutely no technology in front of you. So when I went over the calculator and said, oh, here's a bunch of lists, here's a list of possible rational zeros, let's try a bunch of them out and figure out which one is the zero, so we kind of save our work. The author here is pretending we don't have any of those tools and creating some shortcuts that are helpful. But for us, we don't really need those shortcuts because our shortcut was our calculator to use the table to figure out which ones are zeros. So that's why don't do this Descartes rule of signs and the upper and lower bound properties. Don't worry about that. Just whenever you're asked to factor a polynomial, go through the process that I just described. And that should lead you to the factored form of the polynomial. And that process should work out for everything in this section. The ones that are really crazy with irrational zeros and lots of imaginaries, those kinds of cases are not going to be found here. Right? Any questions? No? No? All right, let's move on then to chapter 4. Awesome adventures with chapter 4. Okay, chapter 4, section 1. We're going to look at exponential functions, graphs of exponential functions, and then compound interest. All right, so here we're going to study exponential functions. Exponential functions are functions where we have a base number raised to a power where the independent variable is in the exponent, right? So here is a prime example, classic example is 2 to the x power. And that very often gets confused with x to the second power. Right, so here the independent variable, the input value is in the exponent to the power of x, compared to here where the base number is the independent variable number and it's being squared. So let's compare these two guys in a table setting so you can see how they differ a little bit. What should we use? Let's see if we can use Excel. Put Excel on here. Excel. Uh-oh. I hardly ever use it, so I don't know if it'll give me some weird. Okay, so we want to compare x to the second power here and compare it to, let's put it over here, 2 raised to the power of x. So we create a table, right? So this is going to be the x value here. So for example, when x is 1, I'll have the input value raised to the power of 2, 1. Let's try a different one. How about 2? That works. 3. Okay. So it's being squared. And then over here, let's let this be equal to 2 raised to the power of this value there. Good. So 2 to the power of 3 equals to 8. All right, so let's make this a little bit larger. About 20. All right, so let's see how this grows. Let's make this equal to this one plus 1. This. Okay, so 3 squared is 9, 4 squared is 16, and now 2 to the power of 3 is 8, and 2 to the power of 4 is 16, so that's how that goes so far. And let's see what happens as this expands a little. So as we grow past that a few values, see how this grows? Let's expand this, it's running out of space. At first it looks like they're both about the same. 3 squared is 9, 2 to the third power is 8, 4 squared is 16, and 2 to the power of 4 is also 16. But then, pretty quickly, the 2 begins to grow much, much faster. See how these values are still relatively small compared to that? Even at 10, 10 squared is 100, and 2 to the 10th power is already 1024. Good. And then so on and so forth. We go over down to 15. 15 squared is 225. 2 to the power of 15 is already 32,768. Right? It's moving down here. Let's go to about something like 50. What's going to happen when we get to the 50? Get at 50. This thing is already out of control big. It's already just using scientific notation to approximate this, so let's just stick to this one. Even on 36, 36 squared is only 1,296, but 2 to the power of 36 is already in the billions. Is that 68 billion, 792 million? Oh wait, is that trillion then? I can't tell. I need commas. That makes it easier. Spaces. Okay, so that's going to be millions. Yeah, 68,719,478,736. So in order of magnitude, close to 69 billion compared to 1,296. Right? So clearly, 2 to the power of x grows much, much faster than x squared. Right? Even though they begin life innocently enough, look similar, 2 to the x power will grow much faster. So that's true for any of the exponential numbers. Exponentials grow much faster with any base than with any base bigger than 1 than its counterpart, where we have the variable raised to that that same power. Good? Questions? No? Okay, so that's all we really want to get out of that. So don't confuse those. Okay, so to study exponential functions, we must first kind of define what it means for it to be some value that has a form a to the x power. When x is a real number, for x being any real number, when x is a natural number, like we just saw, a 2, x to the second power, when we see a counting number or a natural number in the exponent, we can kind of visualize what that means. So we know that 3 to the 4th power means that we're going to have this be multiplied by itself 1, 2, 3, 4 times. And if we have a fractional power, like we saw that this meant that. So if we have 3 raised to the 5 seconds, it's the same thing as 3 to the 5 seconds raised to the 5th power, which means that this is going to be root 3 times root 3 times root 3 times root 3, 1, 2, 3, 4, 5 times. It's one way of visualizing it. But how do we get an actual number out of this thing, other than using technology and getting a value from there? Well, what we want to think about is approximating it so that it gets close to a rational value. Good. So if we want to figure out what is 5 to the power of root 3, right? How do we put an irrational number in the exponent? What does this mean? 5 multiplied by itself root 3 times? That doesn't seem to make sense, right? Or 2 multiplied by itself pi times, right? Again, that doesn't quite make sense. So what we're going to do is just approximate this answer by looking at what happens as we get close to that answer, right? As we get closer and closer and closer to a value of the exponent, we'll get closer and closer to a good approximation. So root 3, for example, is approximately this. So if we want to find out what is 5 to the root 3 power, we're going to think about, well, first of all, what is 5 to the first power? Okay, that gives us a solid answer. Not exactly that one. Okay, but let's think about what is 5 to the 1.7. 5 to the 1.7, well, that's a rational number. That's 5 to the power of 17 over 10. Oops. 5 to the power of 17 tenths. And we know when we have a fractional one, then we can restore it, right? We know how to approximate it this way. So I can tell that. Okay, still not the right answer though. Okay, but then let's figure out, well, what is 5 to the power of 1.73? That's another fractional one, right? As long as it terminates, then I can rewrite it as a fraction. It might be a really ugly fraction. This is 5 to the 173 over 100. But it's nonetheless a fraction, a rational fraction. Okay, so we keep going, and eventually we'll see that there's a pattern as these begin to approach the real answer we're looking for. Okay, does that make sense? Any questions? Good. So when we want to find what is 5 to the power of root 3, we can approximate it by doing 5 to the power of 1.732. If you want to get an even better approximation, well then approximate it by going out to more decimal places here. Maybe approximate root 3 to 4 decimal places, or 5 or 6, and then that'll give you a pretty good approximation. Good. Okay, so there is more sophisticated math out there that can help us mathematically confirm that this process works. But we don't really want to take that side tour and go into that rabbit hole about how to prove that this is true. I think intuitively it makes sense. So this is good enough. But let's try it with pi just to make sure. So the question is, what would be 2 to the pi power? How do we figure out what that is? Right? This is 2 multiplied pi times? Like what? What does that mean? All right, it's 2 times 2. It's supposed to be, uh-oh, it's going to give me trouble. 2 times 2 times 2 times 2, right? And then this thing multiplied by itself, pi times. This kind of definition just doesn't really make sense. Right? What the heck does that mean? This works when we had 2 to the 7th power, right? That was 2 times 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 6, 7. But it doesn't work with pi, right? Okay, so what do we do? Okay, so pi is approximately 3.141592654. That's about as much as I know. Do you guys know there's like contests for people that memorize digits of pi? The winner is like way out there. You should Google it. The most number of digits memorized. It's in like the thousands. People memorize thousands of digits and they win the contest. It's crazy. Anyway, all right, so we know that pi is approximately this. So when we want to find out what is 2 to the pi, well, we begin by something really simple. How about 2 to the 3rd power? I know what that is, okay? And then that's not good enough, though. All right, I want a better approximation. How about 2 to the power of 3.1? We can figure out what that is, right? That's a rational thing. I can rewrite that as 31 over 10, and then I have an answer to that. I know what that can be. And then I can approximate it even more by doing 3.14. And then I can approximate it even more by doing 3.141. And so on and so forth, right? I can just keep going and get as much accuracy as I want, depending on how far out I go. And eventually you'll see that these outputs begin to approximate, begin to get closer and closer to some output, and then you'll be able to get a really good guess at what this approaches. Does that make sense? Okay, like I said, there's some nice sophisticated math to confirm that this process works, but we're not going to go down that hole. But what we want to get out of this is to know that we can always find the answer to any base number raised to any exponent, and that exponent is allowed to be any real number. Okay? All right, so a definition of an exponential function is going to be something of the form f of x equals to a to the power of x, where x is our independent variable. X is allowed to be any real number. And a is also any real number that is positive. We're only going to be focused on the positive end of things. And also not zero. And it's not zero just because then that would be a really boring answer. 0 raised to any power is still 0, so the answer is just 0. Likewise, it's also not allowed to be a positive 1, again, because it's kind of a boring answer. 1 raised to the power of anything is 1, so there's really nothing special happening there. So we really just ignore the cases of a equals to 0 and a equals to positive 1 and focus on all the other positive numbers. Good. So that's our definition for an exponential function. So let's explore some of these things. What does it look like when we have 2 to the power of x, 3 to the power of x, 10 to the power of x? How do we graph them? What do the graphs look like, right? So whenever you begin exploration on something new, you should just think about starting off from basics. What happens when we have a nice little table, and what kind of values do we get? So if we just have 0, for example, this would just be 2 to the 0 power, which is 1. 1 would be 2 to the 1 power, which is 2. 2 would be 2 to the second power, which is 4. Okay, so we begin to see a pattern. Now, with the negatives, it gets a little interesting. We get 2 to the negative 1, and remember that when we have a negative in the exponent, to get rid of that negative, we flip it underneath 1. So 2 to the negative 1 power is the same thing as positive 1/2. 2 to the negative 2 power is equal to 1 over 2 to the positive 2 equals to 1/4. Good. Notice that the outputs are never negative, right? Because if we input a positive number, we're raising it to a positive exponent, we're going to get a positive number. If we're raising it to a negative exponent, then to get rid of that negative in the exponent, we flip it underneath 1, and we still get a positive answer. So there's no such thing as a negative output from this function. Good. Same thing with these other ones. Let's do a couple of values. If we have 3 to the x power, and we have x here, then when x is 0, 3 to the 0 power equals 1 still. 3 to the 1 power equals to 3. 3 to the second power equals 9, and so on and so forth. Negative 1, that'd be 3 to the negative 1 power equals to 1/3. And negative 2, that would be 3 to the negative 2 power equals to 1/9. Right, going that way, so forth. And similar with base 10. Questions? No. Okay, let's evaluate some of these things. Using technology, it says. All right, well, using technology. So for part A, we have f of 5. So the f function is this. Must be 3 to the 5th power. So we can use technology to figure out what that is. For part B, well, I guess I can just put it on here. Let's use this. So this one is going to be 3 to the 5th power. This one is just going to be 3 to the pi power. This one is just going to be 3 to the root 2 power. And this one is going to be 3 to the negative 2/3 power. So really we just want to practice or make sure you know how to use your calculator to find these answers. Let's use our calculator to find these answers. Okay, so let's get our calculator out. Wherever you start off in your calculator, you can hit this button, quit, second quit, to go back to the main screen, hit clear. And so 3 to the power of, this little caret symbol up here is the power, to the power of. Now in my calculator, it does this little thing where it goes up to the exponent and has a little box, and then I can type in the 5 up there. So it's sort of the newer user interface. But a lot of the older calculators are going to have this little caret symbol that appears there, this symbol. So if yours works that way, just know that when you see that little caret symbol, it means that you're raising it to that power. Okay, so next, how about 3 to the power of pi? To the power of pi, and pi is right above the caret symbol, so hit second, and then that caret symbol, and then enter. I get that. 3 to the power of, and then I would wrap it in parentheses. We have negative 2 divided by 3, close the parentheses. Let me get that. And then 3 to the power of, parentheses, and now we have the square root of 2. We can use this little square root number value right in here. So square root of 2, close parentheses. Go out here, close parentheses. So delete this guy, like that. And close parentheses. Enter. Okay. And your Yeah, okay, so here, this little caret symbol, this is how the little exponent will appear for a lot of you guys when you type it in. So just making sure people know how to use your calculator. Does anybody have any problems with their calculator right now? Typing these guys in? No? Okay, graphs of exponential functions. So, let's look at these two functions. Let's try and graph them and see how they're related to each other. In order to graph anything, we begin with a table. So again, I'm going to start off with the table of x and 3 to the x power and do some values there. How about evaluate it at 0, at 1, at 2, at 3, dot, 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 -1, -2, something like that. As we saw before, this one represents 3 to the 0 power, which is 1, 3 to the first power, which is 3, 2 to the second, 3 to the second power, three to the second power, which is 9, 3 to the third power, which is 27, and so on and so forth. 3 to the -1 power equals to 1/3, and 3 to the -2 power, it's starting to give me trouble, 2 power, which is equal to 1/9. Good. Okay, so we have all these ordered pairs from here. We have, just when I thought I wasn't going to have trouble anymore. -2, comma 1/9, -1, comma 1/3, 0, comma 1, 1, comma 3, 2, comma 9, and 3, comma 27. Good. All right, how does that compare to the other function? So we have this other function. Let's create a table over here. X, and then we have 1/3 raised to the power of x. So 0 is easy because anything raised to the power of 0 is still going to be a 1. 1 is easy because 1/3 raised to the power of 1 is going to be 1/3. Negative, oops, not negative, +2, also easy because we have 1/3 squared, which will be equal to 1/9. The other direction, -1, I have 1/3 raised and then one fraction divided by another fraction. We simplify this by multiplying the numerator times the reciprocal of the denominator. This thing just turns into 3 to the power of 1, just 3. Good. -2, then we have 1/3 raised to the -2 power, which then turns into 3. You can also do this. This 1/3 is the same thing as 3 to the -1 power raised to the -2 power. Okay, let me put that in color. This part in here, and this part in here. Color. 1/3 can also be written as 3 to the -1 power. And now when we multiply the exponents, we end up with 3 squared, which is equal to 9. Good? Any questions? No? 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 Okay. So notice the relationship between these two. As the input goes bigger and bigger and bigger and bigger, as x goes to infinity for this function, the outputs, y, are heading toward infinity too. They're growing out of control. As x goes toward negative infinity in this function, the outputs are going to be getting smaller and smaller and smaller. Right? 1/3, 1/9, the next one's be 1/27, 1/81. So these things are growing toward 0. They're getting smaller and smaller and smaller. The opposite is true here. as the input gets bigger and bigger and bigger and bigger and bigger, as x approaches to positive infinity for this function, the outputs are getting smaller and smaller and smaller. The outputs here are heading towards 0, whereas over here, as the inputs are heading toward negative infinity, right? Because we have a fraction 1/3 raised to a negative exponent, then this thing is heading toward positive infinity. Good? Questions, comments? All right, so let's look at the graphs. Let's use Desmos. Desmos to create the same thing. So before we know how to graph anything, then we'll just start off with graphing a bunch of ordered pairs. Let's create a table. I need you to be fancy. Let's put you there. And let's use 3 to the power of x. All right, so 0, it leads to 1. 3 to the 0 power is 1. So that's this dot right there. Okay, then when I put a 1 in there, I get 1 comma 3. 3 to the 1 power is 3. And then when I put a 2 in there, I'm already jumping to 9, which is way over there. So I'm starting to get these 3 dots. I can also do -1. -1 leads to 1/3, which is 0.33333. That's this dot. -2 leads to 1/9, which is 0.1111111. That's this point. -3 leads to this 1/27, which is 0.033. Okay, so you see it's getting really, really small fairly quickly too. Okay, so we start to see a shape. Luckily, since we have technology, we don't have to stick to just counting numbers, natural or integer values. We can find some decimal values to fill in this graph. So how about 0.2, 0.4, 0.6, 0.8, 1.2, 1.4, 1.6, 1.8. Right? How about some other values over here? How about -0.2 and -0.4 and -0.8? Okay, so you start to see what the shape looks like. It's going to have this sort of a shape. Good, so then we can just jump to the calculator graphing it. Power of x. And let's make it green. Okay, so if I keep going and I find an infinite number of dots here, every possible input value that's in the real number line, then I will get an infinite number of ordered pairs when I graph them, and all those ordered pairs will eventually begin to look like this smooth curvature, which is really an infinite number of ordered pairs that satisfy this equation. Okay, so this is the graph of 3 to the x power. Any questions? No? Okay, so we could do the same thing with 1/3. Let's go over here. Let's get a table going. X is fine. Parentheses 1 divided by 3. 8 to the power of x. Okay, so 0 still leads to 1. Let's make it a different color. Let's make it orange. So 0, 1 is still a value. 1/3 to the 0 power is still 1. And then when we put a positive 1, then we get a 1/3. When we put a 2, then we get a 1/9. When we get a 3, then we get a 1/27. So that's these values right here. Right, this is 1/3 raised to the 3rd power is 1/27, which gives you this decimal. 1/3 raised to the 2nd power is 1/9. 1/9 is 0.11111. And this is when we put in a 1. 1/3 to the 1 power is 1/3, is 0.3333, and here's 0.1. Okay, so you can see it's getting smaller and smaller and smaller as the input values go toward positive infinity. The outputs of this function are going to get smaller and smaller and smaller. Okay, in the other direction, if we type in a -1, we get a +3. If we type in a -2, we get a +9 up here. Good. And again, just like before, we don't have to stick the whole number since we have a nice computer to help us. We can fill in the blanks with some decimal values. How about 0.2, 0.4, 0.6, 0.8, 1.2, 1.4. Okay. How about some negative values? How about -0.2, -0.4, -0.6, -0.8, -1.2, -1.4, -1.6. Okay, so I start to get a bunch of ordered pairs, and it doesn't take long to hopefully convince you that if I kept going, I found an infinite number of those dots, eventually that graph will look like this. 1 divided by 3, close parentheses, the power of x. Looks like that, and let's put in orange. Here's orange. There we go. So if I kept going and I found an infinite number of dots, every possible input value that's a real number, plugged it into this little thing, eventually all those ordered pairs will give me this orange shape here, this orange curvature. So eventually we get rid of the individual dots and go, okay, this curvature is the graph of this equation. And notice how it relates to the graph of 3 to the x power, right? The green one is 3 to the x power. The blue one, the orange one is, let's get rid of that. Let's get rid of that. So the green one is 3 to the x power. The orange one is 1/3 to the x power. Good. Questions, 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 questions? That can also be seen if we kind of play around with the equations themselves, since we know all about transformations from a prior section. Let's make a little space here. Since we know all about transformations from a prior section, we know that if we have f of x equal to 3 to the x power, and then we have g of x equal to 1/3 to the x power. As we said, 1/3 can be rewritten as 3 to the -1 power raised to the x, which is equal to 3 to the -x power. So that's just this function evaluated at -1, f of negative x. Right? If I took this function right here and I plugged in a -x, I would get 3 to the -x. So these two are related this way, and we know from before that this is a reflection about the y-axis. F of x reflected about the y-axis. Any questions? Good, kind of, sort of, kind of. Okay, so here's a table of the same things we did. We put in some input values. We raised 3 to the power of those input values. We got some ordered pairs from those. If we graph them, we will slowly be able to create this red one. We also did 1/3 of the x power, tried some values, get some outputs. If we graph them, eventually we get that. And we see that they are a reflection about the y-axis of each other. Good. Which we can do right here. To confirm that they're a reflection about the y-axis. If we do it for multiple values, we can see that this is true. Right? So let's use Desmos to kind of isolate what this means. So we had 1/3 and 3. We can also have y equals to 2 to the power of x. And of course, it's going to look like that. And if we have y equals to 1/2, oops, 1 divided by 2 to the power of x, it's going to look like that, right? So they're always a reflection about the y-axis. Whenever the base number is a number bigger than 1, it's going to have this sort of general shape always. It's going to go through the point 0, 1, no matter what, because no matter what the base is, raised to the 0 power will always get 1. But as that base number gets bigger and bigger and bigger, like maybe that becomes a 5, maybe that becomes an 8, maybe that becomes a 13, right? As that base number gets bigger and bigger and bigger, then it grows toward infinity faster in this direction, and then over on this direction, it grows towards 0 faster, right? That's what happens as the base number gets bigger and bigger and bigger. And then all we have to do to find its mirror image is to turn it like that. So now that's a perfect reflection about the y-axis, these two. Good? Questions, questions, questions? So we can have a slider situation here. How about equals to a to the power of x, where a is a slider. So if a is a value that's bigger than 1, like this, it grows and grows and grows and grows and grows and grows. See how it always has that same general shape? It just gets steeper and steeper and steeper the bigger that base number is, like this. And then when we get to 1, the output is silly because 1 raised to the power of x is always 1. So 1 is just a flat horizontal line, right? 1 to the x power is just 1. So it's just the line y equals to 1. And when we get to a decimal value between, let's put 0.01, and let's make this 10, 5.1s. So then as we go to decimal values between 0 and 1, then this thing begins to flip in the other direction and have a shape that looks like this. Right? So it looks like this, and then it flips the other way. And it looks like this, and then it flips that way. Any questions at all? So this way means that the base is bigger than 1. This way it means that the base is between 0 and 1, not negative, right? We're not allowing the base number to be a negative number because that has the potential of having irrational numbers and weird things that could happen. Imaginary numbers, I should say. Questions? Good. So it's kind of hard to spot here, but this yellow one and this purple one are reflections about the y-axis. The purple one is 10 to the x, and this yellow one is 1 over 10 to the x power. Notice that they all go through the point 0, 1. This blue one is 1/5 to the x power, and then over here in this blue, we also have x 5 to the x power. Wait, how come? That's weird. In some cases, they left the colors. Anyway, their color scheme is a little weird. Any questions? No? Sort of? Kind of? Sort of? Kind of? Right? So when the base number is bigger than 1, the graphs will have this sort of a shape. And as x goes toward infinity, the outputs will go toward positive infinity. And as x goes toward negative infinity, the outputs will go toward 0. Right? That's when the base is bigger than 1. When the base is between 0 and 1, it's a reflection about the y-axis, and then the opposite happens. As x goes toward positive infinity, the outputs go toward 0. As x goes toward negative infinity, the outputs go toward positive infinity. But notice that they all go through the point 0, 1. And also notice that there's never a negative output. The outputs are always positive no matter what. Good. So we generalize that in this kind of table. right? Whenever the base is bigger than 1, this is the general shape of the exponential graph. Always. We just have to figure out just how steep this goes. The bigger the base, the steeper it'll go, the faster it'll grow toward infinity, the faster it'll grow toward 0. And when the base is a value between 0 and 1, then it has this sort of a shape, right? It always still goes through 0 and 1. It's just a matter of determining how steep that curvature is. Questions, 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 questions? No, no, no? Okay, so let's say, for example, we wanted to find the exponential functions of the form a to the x power to these guys. If this was all that's given. Well, from here we can tell that whatever this is, it must be something of this form, and we can tell that f of 2 leads to 25. So that means that some number being squared equals 25. We can take the square root of both sides and see that this is plus or minus root 25. Which means that this is equal to plus or minus 5. But in exponents, we never allow this to be negative, so we ignore the negative. Ignore the negative. And so we get to conclude that this must be the exponential function f of x is 5 to the x power, right? And confirm that when we put a 2 there, it works out. Good. On the other hand over here, that must mean that f of x equals to a to the x power, and we have that f of 3 led me to 1/8. Good. So it must mean that a to the power of 3, some number raised to the power of 3 must be 1/8. We can raise both sides to the power of 1/3. Which means that a must be equal to 1/2. A must be 1/2. So we have f of x equals to 1/2 raised to the power of x as our function for this guy. And this is the function for that guy. Any questions? Cool. What happened? So I'm having some computer issues here. Skipped a bunch of things. 24, 25. Okay, so this is the work we found already. Solutions for that. Compare the rate growth of these two functions. I already did a little bit of that to show how much faster this grows when compared to that. So don't confuse them. And compound interest.